Hi. My name is James Titcumb. I come from United Kingdom, and I've been doing PHP since 2002, programming since before that, Zen certified engineer, contributor to many open source projects. I'm on the Zen Framework Community Review team, and I'm also a consultant engineer at Roave, with the dog head. So, to understand about static analysis, we need to know how PHP works, right? So I'll just give you a quick overview of how PHP works and how the PHP code is fed into Alexa, which generates tokens. Tokens are fed into a parser, which results in an AST. The AST is compiled by the compiler, which generates opcodes. The opcodes are stored in the op cache and executed in a virtual machine. Everyone with me so far? Some nods, actually. I was surprised. That's fine. That's fine. The virtual machine is not like Vagrant or anything like that. It's a virtual CPU which executes opcodes and executes them, right? So the AST step is new, or was new in when PHP 7 came out. So let's first have a look in a bit more detail what actually happens here. For those of you who are like, what did you just say? We can try and understand about how this is all put together. So the first step is the lexing, right? And lexing is, it's the literal sense of the word. It's trying to make sense of the words that it sees in the file, right? The lexer itself is a generated C program. It's generated by another program called re2c, which is known as Alexa generator. So we have this definition in zen-language-scanner.l, which describes how tokens are supposed to be split out. So that defines like what the words are. If you're thinking like a normal language, this will say, house is a word or tree is a word, yeah? The format is kind of similar to fast lexical analyzer, which is used by HHVM as well, and amongst other programming languages. Here's a few examples, fairly straightforward, I think. The lexer is a state machine, so as it progresses through your code, it changes state. So the first part in the angle brackets here is basically what state you need to be in for this particular token to match. So a certain token will only match in a particular context or state, right? This particular one is when we're scripting. That's the normal default state. There is other states like I'm inside double quotes or I'm inside here doc or now doc and things like that. So we can have different expectations there. The next part is the token itself. This is just basic strings in these cases. There's nothing too complicated. Exit, die, and function. And inside the curly braces is what actually happens when the lexer encounters these tokens. So when we see the word die, and we're in the scripting state, we're going to return a token called tExit. Now, if anyone's played with tokens in PHP before, you'll be familiar with like all the tokens are defined as constants, like t underscore whatever the name of the token is. So you may have seen these before. When we return the token, we are actually just saying output this token to the token stream, right, which is given to the next part of the process. So yeah, the state allows the same tokens to be used as well in different ways depending on the context you're in. So let's have a look at a little bit more of a complex example to understand what that means. So this particular token, $ open curly brace, this will only match when we're in double quotes, backticks, or in here doc. And so when we encounter that token, $ open curly brace, we're going to change the state, right? We're going to say, now we're looking for a variable name. And we'll also return the token to the token stream so that we know we've encountered the $t open curly braces. The second part is the closing part of what we've just done there. So we're going to be in the looking for a variable name state, right? We look for a label, which is basically a shorthand definition, followed by a curly brace, right? What we do now is we need to copy the semantic value into the token stream and give that token some actual context. In this case, it's the name of the variable we're putting into the string. Okay? And then we change the state back to scripting. And we return the token. Okay? So given that syntax definition, we can pass that into this tool called re2c, and it generates a C file. You can do this yourself. You can check out the PHP source code. You can run re2c with a load of flags, which are almost impossible to remember. And the generated C file, you will see, has like 8,000-ish lines of utter nonsense, right? It's got really badly named variables and things like that. So it doesn't actually make any sense, and there's no point in trying to make heads or tail of it. What is important is what's in the definition, and then later on we can use that program within PHP. So the parser is the next step. So the output of the lexer is this token stream I mentioned, and that is the input for the parser, right? And it works in kind of a similar way, right? It contains a parser definition, which might look something like this. It starts getting a little bit more complicated, but a real language is more complicated, right? Because if I just start throwing words at you, like house, tree, building, it doesn't make sense, does it? It only makes sense when I put those words in the correct order, so that they have meaning, semantical value for you. So this is what the parser does. It makes sure that the tokens, the words that it's been given, are in the right order and make sense. Okay? So just have a look at this particular example and sort of break it down and see what parts there are. These couple of definitions describe an if statement, right? We've seen if statements. We know how they work. So we've got two definitions. We've got if statement and if statement without else. I've not put on the definition for things like an expression or a statement because they're huge, right? I can only fit so much code on a slide, and it's not really that interesting to read through huge lines and lines of definitions. So we'll look at the if statement. So what this says is I will match an if statement if I encounter an if statement without any else. And we have some precedence operator there to say that the operator is left associative, if that's interesting for anyone. Or we match an if statement without else, followed by an else token, followed by a statement. Okay? But to understand what an if statement without else is, we need to look at its definition. So you can see there's a bit of recursive descending down going on here. We'll match if we get an if token, followed by the literal open parenthesis, followed by whatever the definition of an expression is. I think we know what an expression is. Followed by a closed parenthesis, followed by a statement. And the definition's not here. One interesting point to note is that curly braces are actually part of a statement. Okay? Or we also match if we encounter an if statement without else, so there's some recursion going on there. Followed by an else if, followed by an open parenthesis, an expression, close parenthesis, and then a statement. Okay? So what this allows us to do is, by using this definition, we can say, well, you can have an if, and then an else if, and then an else if, and any number of else ifs, followed by an else. Or you can have just an if, or you can have an if and then an else, and so on. So let's use these rules to parse and understand this if, else block, right? The first block matches if statement without else, right? Because it's an if statement, it doesn't have an else. It's got if token, open parenthesis, expression, close parenthesis, statement. The purple block here also matches if statement without else, but it matches the second alternative grammar for this. It matches an if statement without else, followed by else if, followed by literal open parentheses, expression, close parenthesis, and a statement. Finally, the red block matches the grammar defined in if statement, okay? Because it matches the second grammar, specifically. It matches an if statement without else, followed by an else token, followed by a statement. And like I said, the statement includes the curly brace, so that's what we're actually matching there. So let's go back to the definition. This is way back from PHP 7. And notice these curly brace parts, right? So much like the Lexa had curly brace and say, this is what we do if we meet this particular token, we're doing the same here, right? There's something interesting to point out here. We're calling this function zend add ast add list, right? Or list add, sorry. And then in the second one, we're doing zend ast create list, zend ast create. And all these functions are to do with the abstract syntax tree. If we have a look at PHP 5.6, before the AST existed in PHP, this is what it looks like. I mean, the grammar is actually slightly different because some of those definitions changed to be better written, right? But notice within the curly brace, we've got this function zen do if cond condition, right? And what this does is it generates the opcodes directly. So that's we're missing out this AST step, okay? So the AST is new in PHP 7 and above. And going back to the very first diagram, right, the result of the parser in PHP 7 is the abstract syntax tree. The abstract syntax tree is then what gets fed into the compiler, which then translates things to opcodes, and then the opcodes are executed in the virtual machine. Okay, anyone not with me so far? A few. Okay, fine, that's fine. We'll try and simplify a little bit more. First of all, I haven't actually said what an abstract syntax tree is. The name might sort of give away it's a tree, right? Absolutely, it's a tree. AST stands for abstract syntax tree. It's a representation of some code, okay? It's not specific to PHP. This is not a PHP concept. It's not certainly not a new concept. It's existed in writing programming languages for probably as long as writing programming languages has pretty much existed. The AST is a data structure, right? And it represents your code. It can be modified, of course, right? You can modify data structures, and actually then you will modify the behavior of the code. It also contains metadata like what line and what file this particular piece of code is and so on. And your AST can also be unparsed. That is to say, we will take your abstract syntax tree and generate code from it, because it represents code. The layout will probably change, but it doesn't contain much information about layout and so on. Doesn't matter. It's representing the behavior of the code, right? So this is a script we'll produce some AST for. I think it's fairly clear what's going on here. Represented as a tree, right? We will take the echo statement, and the echo statement has a child node, which is the scalar string hello world, okay? Fairly straightforward, I think. Now, if we add a bit more complexity in here, not very much, we're just going to do a concatenation, right? But there's a little bit more going on here, right? We've got these new types of nodes in our tree. We've got our echo statement, but this time the child node is a concatenation. The concatenation is a binary operator, which means it has a left and a right. It has two operands. So the left one is the scalar string hello, and the right one is the scalar string world, right? And an awful lot of things in programming languages are binary operators, right? They have two arguments. Add, for example, right? You have two things, add left and right, subtract, and so on, all the mathematical things, right? So let's do some maths, right? Let's do a bit more of some code. We're going to assign $A with the value 5, $B with value 3, and we're going to do a sum, right? $A plus brackets $B times 2. So the AST gets a little bit bigger for this, so sorry if you can't see it, but let me explain what's going on here. We've got our assign statements. They are statements within their own right. They are represented in the AST as well. We've got then our echo statement. The child node is an add operation. Like I said, add is a binary operator as well, so we've got a left and a right. The left, in this case, is the variable $B. We don't know the actual value of that when we're looking at just the echo statement. Obviously, we look up a little bit and we can see it's assigned. And the right-hand one is the integer with a value 2, right? Because we're multiplying it by 2. So why has this AST come around? Why does it now exist in PHP? Well, it's mostly for internal reasons, right? It decouples the compiler from the parser, which means that we get better maintainability and code quality inside PHP. Probably going back several years, we'd look at PHP source code and be like, I don't know what's going on here. I mean, in real terms, it's just lots and lots of macros, but hey, that's fine. But what this also means is we've got slightly simplified productions in the parser as well. So I like simple. Simple is good, right? And it's also faster, asterisk. And I have to put the asterisk because it's faster in a very specific part of compilation, right? Despite the extra step, it does have a very small performance increase. Now, the runtime performance is negligible, right? It doesn't make much difference because by the time we're in runtime, everything's in the op cache anyway. It's actually getting the code from your files, your PHP files that you've written, into the op cache. That part of the process is faster. It's about, some people say with the wild benchmarking, that it's 10 to 15% faster maybe, right? But it requires more memory, well, because we're building this big old tree, and these trees can get really big. I mean, you saw with just that simple math sum, it started getting quite large already. So the data structure as a tree it's very efficient for node traversal, right? We can do things like statically collapse nodes and maybe do some optimizations in the future. Some languages use AST to do optimizations. PHP doesn't really do much of that because most of the optimizations have already been done when we have opcodes, right, by the compiler. So looking at that sum with the assign and the echo and so on, we can display it as a tree, right? This is all the exact same information. We've just now drawn it as a nice, pretty tree. Hence the name abstract syntax tree. But when we look at this, we can start doing things like following a line around the tree. We can start at the top with the statements, and we go and we hit assign, and we can hit the variable, the scalar, and so on. And we can execute, if you like, each node we touch in order. All right, so we start at the top, go left, descend down, and this is what's called a pre-order traversal. If you write down everything you encounter in order, you'll get something that looks like this. The important thing is that the operation, right, or the statement is prefixed. It comes first, right? The arguments, or the operands to the operations, are after. And we're used to seeing this, right? This is how we write code, isn't it? You call a function, you pass parameters into it. So we're used to seeing this kind of pattern. It's called Polish notation, and it allows us very easily to see something important, which is the order of precedence. When writing a programming language, the order of precedence is hugely important, because when we have a sum like 1 plus 2 times 3, and if we put aside like the rules of mathematics, because we know the answer to this, right? But is it 7 or is it 9? Because depending on which operations you execute first, you're going to get different results. Obviously, mathematics has defined what the correct answer is here, because they've defined the order of precedence for us. But so when we write this out using Polish notation, and this looks a bit weird because actually we're not used to seeing mathematical sums like this, which is kind of funny because we're programmers, right? We should be used to this. What we're doing is we are doing an add, and the first parameter is 1, and the second parameter is another 1. So, yeah, there we go. I forgot to put the slide up. So yeah, reading left to right, you get your add operator, you get your 1 is the left operand, that's easy, and the right operand is a whole other operation. So we have to evaluate that first. And then that's pretty straightforward. The operator is multiply, so that's like your function name. And then your parameters, your 2 parameters for that function are 2 and 3. So in order to find the whole sum, you have to figure out the inner sum first, and then go back up the tree and find the outer sum. So there's something else called reverse Polish notation, which is the other way around. It's not completely the other way around. It's not just reversing the string. It's similar. But to parse this, we build a stack, right? So the values come first, in this case, and the operand operates on the last two things in the stack. In order to build this reverse Polish notation format, instead of that pre-order traversal we do what's called a post-order traversal. So we visit all the leaf nodes first, and then come back up the graph, adding all the rest of the nodes. So let's have a look at how we might execute this, because, well, 1, 2, 3 times plus doesn't seem to make any sense, but it does actually to a computer, a lot more sense, in fact, than normal Polish notation. So we step through each item. If it's an operator, we execute it, otherwise we push it onto the stack. So I've drawn a nice little picture of a stack. I'll show the stack and what's in it in each part of the process. So the first thing is just a value. So we're going to add that into the stack. We push that onto the stack there. The next one is also a value. So we push that onto the stack. Also a value, so we'll push number 3 onto the stack. So then the next one is an operator. The operator, we know multiply takes 2 things. So we take 2 things off of the stack, 2 and 3. Right? Those are the last things that we put onto the stack. We perform the operation using those 2 operands, and then we push the result back onto the stack, and we get the number 6. The last one is also an operator. It has 2 things. So we'll take 2 things off of the stack, add them together, push the result onto the stack, which is 7, which is the correct answer, of course. When you've reached the end of the input for a particular statement, the final result is the single item left in the stack. If there's more than one item on the stack, or there's no items in the stack, then something's gone wrong. So this is kind of the definition difference between an expression and a statement, right? So we can write a compiler now, armed with this very dangerous knowledge, in 3 easy steps. And we'll write it in PHP because this is a PHP talk. Don't use it in production. And also, this is not very optimized code at all. It's just for educational purposes and having a bit of fun, right? So if you like, you can follow along. I have this code written in my GitHub, github.com/asgrim/basic-maths-compiler. It'll be there somewhere. And this is the code that we're using for this particular presentation. OK. First of all, when we write a programming language, which is essentially what we're doing, we have to define the language. We have to say, well, what does this language look like? Our language is just going to be basic sums, right? We're just going to do mathematics. We're only going to use positive integers as inputs. We're going to allow white space, but we're going to ignore the white space, so it's meaningless. That's the same as in PHP, right? And we're going to have just 4 operators: add, subtract, multiply, and divide. We're also only going to support 1 line of input. That makes things a little simpler. And there's also going to be no way to override the order of precedence. So there's not going to be like parentheses which allow you to, say, execute this particular operation before this one, and so on. So I'm doing that because it makes it much simpler. So we'll write a simple lexer. You can write a lexer with just regular expressions, because that's what you're doing. You're just matching tokens, right? First, we define what the tokens should look like. An add is going to look like the add symbol. The minus is going to look like the minus symbol, and so on. We also have to define what an integer looks like, and also what white space looks like. Like I said, we're going to include white space, but ignore it. So just want to note, for those of you who aren't like regular expression gurus, all of these statements have the circumflex at the start. And that means that we're only going to match the very start of the string. So it means we're not going to match something later on by accident and make things go wrong. Okay? So what we're going to do is we're going to take our inputs, that is our code, right? We're going to analyze from a particular offset which starts at 0. That's a good place to start. And each time we match something, we move the offset on by the length of the lexeme. The lexeme is the actual string that was matched. So for example, the number or the piece of white space or the operation, right? The matching method is pretty straightforward, right? We run a preg match. There's nothing too complicated here. We're actually just looping over all those regular expressions and say, do we match any of these? Yes? No? I don't know. If not, if it doesn't match something, then we've encountered a syntax error, okay? So we throw an exception. And that's how syntax errors happen, right? The basic ones. If we do match something, we're going to return an object, the token, and the matches one is the lexeme itself, right? So step 2, parsing the tokens. We've done the lexer, that was it. So as I mentioned, order of precedence or operator precedence is very important. So we need to define this so we know how our language is going to work. So we're going to use the standard operator precedence of mathematics. In this case, multiply has the highest operator precedence, so we put that the highest number, and subtract is the lowest, and obviously we've ordered them because ordering makes sense, right? We could, of course, do this in a wrong order, and we get different results. And obviously, if you do that sum earlier, the 1 plus 2 times 3, you're going to get different results if you change that order of precedence. So we're going to loop over the tokens, and we've got 2 stacks, right? We've got just a normal token stack, an output stack, we'll call it, and a temporary operator stack that we're going to use. Now, if the token that we encounter is an operator, we're going to go off and have a look in a bit more detail, because there's a bit more code going on here. So each operator is pushed onto the operator stack. However, on each iteration, we then check and say, well, is anything in our operator stack the first thing, usually? Does it have a higher operator precedence? If it does, then we're going to pop it off from the output stack and push it, operator stack, and push it onto the output stack. At the end of the function, we'll loop over any operators that are left and push them onto the output stack. And what we end up with, right, let's have a look at how this works. So we've got 1 plus 2 times 3, which is something we understand. That's our input code. So let's step through this bit by bit. The first token is a number. It goes straight onto the output stack, right? The next token is the add operator. It's an operator. While we do that, we say, oh, is the last thing in the stack higher precedence? No, there's nothing in the stack, so there's nothing of higher precedence. The next one is a value. The next one is an operator, so we put it on the operator stack. We look at the stack and say, does plus have a higher operator precedence than multiply? No, it doesn't. Okay, so just add multiply onto the operator stack. Next one's a number. All right, so we add that onto the output stack. Now, we finished the input, so we need to loop through the operator stack and put them all onto the output stack. Multiply and then plus. And hey, this is reverse Polish notation, right? So we've now taken the tokens that we've got in our code, and we've changed the order of them to something that is meaningful for our next part of the step, the parser. Right? So we're going to create the abstract syntax tree. Now we've got a stack of tokens in reverse Polish notation, so we can use a very simple stack compiler pattern to take those, to progress through the tokens that we've ordered and make a tree out of them. So IP, $IP is the instruction pointer. It's not actually used in this particular piece of code, but this instruction pointer allows us to actually navigate around backwards and forwards, which is useful for when you introduce things like parentheses to change the order of precedence and so on. Or if you've got arrays and things like that, then you can go backwards and forwards as necessary. So if it's a value, it's very simple, right? We just get the lexeme, we convert it to an integer, because it should all be a positive whole integer, and put it onto the AST stack. And that's it. That's very straightforward. If it's an operator, we pop the last two values from the stack, like we did earlier, and we push them onto the operator node, right? And then we add the operator node to the stack. And we end up with something that looks like this. And this looks a bit more like code, right? Except the add and the multiply are functions, if you like, instead of just operators. All right? So now we've got our AST. This is the really easy part, right? We're going to execute it. Basically, this is the virtual machine part, if you like. And we can execute that directly. So we're going to descend through the tree and execute it as we go. So we have a function called compile node, right? So we give it one node, that's our statement, right? Because we only have one line of input, so there's only ever going to be one statement. Otherwise, you'd have an array of statements or something. If it's a binary operator, we're going to call another function we'll look at in a moment. If the node is an integer value node, then we're going to just return the value, right? We don't have any other nodes, so that's it. So let's have a look at how the binary operator works. This is where the recursion comes in, right? So when we have a binary operator, we have our left and right, right? We've got our two operands. We don't know what the left and the right are. They could be just numbers. But they could also be operators in themselves with operands attached to them. So we actually have to pass that node into our compile node function and find out what the value is, right? So we need to pass that node to compile node again, and that's where the recursion comes in. So we've compiled left and the right operands. Once we've done that, we just execute the appropriate sum. And of course, of course you can change what each operator actually does, and you could make add do a subtract, and subtract do an add, some weird funky things, and obviously then you're going to get unexpected results. Although it would be expected, because that's how you define your language, right? So that's how we compile it. So what does it mean for me? What does this AST thing mean? Well, on the surface, it doesn't seem that relevant to my day-to-day work, does it? You get faster, more efficient code, right? Well, that's good. Yeah, that's slightly irrelevant, right? AST is one of the reasons that PHP 7 is slightly faster. Actually, most of it's other optimizations that are done. But there is scope for improvements to be done in PHP with the AST, right? We can do some optimizations, perhaps. Also, knowing how the engine works is kind of interesting, and it can be helpful. I would caveat that with saying that don't just change the way you write your code to suit the compiler, because the compiler does a very good job of reading your code and running it as fast as it can. It can take some really rubbish code and make it run really well. So, as I mentioned earlier, AST is not a specific concept to PHP. And hopefully it's helped you understand how other languages actually work. Because most of the standard programming languages like PHP, Java, and whatever else, they all work in the same way. They generate this abstract syntax tree. So what about using the AST in userland, right? What use could I possibly have from that? Well, it allows us to get good insights into what's going on in your code, right? It allows you to examine the structure and say, oh, my class, it looks like this, it has these properties, and so on. Which is fine, but your eyes can see that. But as other talks in this conference, and I won't make any assumptions whether you've seen things about static analysis and so on already, you can do things like static analysis and magic things and get a real insight into what's going on in your code. So there's an extension for PHP 7 up called PHP-AST. It's written by Nikita Popov. It exposes the AST to userland. The downside is it requires an extension to do this, right? So you have to install an extension, which for some people is like, oh, that's fine. I can just install an extension. For other people, they're like, well, it's a bit of a hassle. Yeah, fine. This is roughly how it works. You once you have the extension installed, of course, you can call this AST parse code function. You give it a string with some code in it, and it will give you the abstract syntax tree. Now, what's interesting is this particular extension, it uses the same code that PHP uses to generate the AST. So the AST is actually as close as you're going to get as a representation of what PHP uses to be compiled as you're going to get in userland, right? AST dump function is just a function that helpfully displays it, because AST for any kind of even slightly complicated code, or more than a few lines of code, is going to get really big and complicated. So there is also another extension called AST Kit. It's written by Sarah Goldman, and it actually allows modification of the AST, right? So I mentioned at the start you can modify an AST. Just using PHP, you can't. If you have this extension called AST Kit, you can. And then you can execute it, and so you get this thing called monkey patching, right? Which is quite cool. There is downsides, though. It's an extension as well, so you have to compile it or pull it from Peckle, probably compile it. I don't think it's in Peckle. I'm not sure. And it's also deprecated, right? So it was basically just an experimental extension, right? So it's not something we can be relying on, and so on. An example usage of it, though, we can say, well, if true, echo, this is a triumph, else the cake is a lie, right? We load this, we parse this string, right, in much the same way as the PHP-AST extension. And then we execute it the first time, and then we do some modifications, right? We change the true to a false. And obviously, when you execute it the second time, you're going to get a different result. All right, so that's the monkey patching aspect of it, which is kind of interesting. So then there's PHP Parser. PHP Parser is a library written in PHP that was written by Nikita Popov as well. Now, it's more or less the same as the extension. It does this, it achieves the same goal, but it's written in PHP. The upsides are, well, because it's not an extension, you can now just pull it down with Composer and start using it to have a look into your code. There is a big downside, though. It's really, really slow in comparison to actually running this in C. I mean, that may be optimized in the future, or crazy things that people like Anthony Ferrara are doing and writing PHP compilers and whatever else, I don't know, black magic that he's doing. Yeah. But at the moment, if you do a side-by-side comparison of generating an AST using PHP Parser, it's going to be a lot slower. But there are big benefits to this, right? Let's have a look at how it works. It's pretty much exactly the same, right? So you... Okay. No? Okay. So you give it some code, you parse it, and it gives you an abstract syntax tree, right? And, well, what can we do with that, right? We could do something like write a library called Better Reflection, right? We wrote a library, sorry, shameless self-plug. It was written by me and Marco Pivetta. In short, it's the reflection API, the same reflection API that is in PHP, but it uses the AST instead, which means it's very flexible and powerful, I think. And it allows you to do monkey patching as well. Roughly, this is how it works, right? We get something called a reflector, which is the public API. We have something called a source locator, because, well, we might want to be able to reflect from just a string rather than actual code in a file. You can use just a file, of course. That's one of the source locators that you can use. We pass the code into PHP Parser. And finally, from that, we use that AST to simulate what the reflection methods do in PHP. So we tried to keep Better Reflections API as similar as possible, but it's quite similar, but not exactly the same. In the core reflection API, you'd say reflection is a new reflection class, give it the name of the class, and so on. And then most of the API matches, but the creation of the reflection is slightly different. So using Better Reflection, we have this class that you can call. It reflects, you call class reflector, and we use some sane defaults, right? So you can override how this actually works under the hood. The defaults would be something like a PHP internal source locator, so you can reflect on PHP internal code, or evaled code if you're evil enough to be evaling things. And then your autoload source locator, which is basically it hijacks the old autoloader when it tries to instantiate a class, and it grabs where that code is coming from. So it's kind of clever, but slightly, it's not always going to be perfect. The source locators, it's the instructions for Better Reflection to find PHP source code. So that source code is then fed into PHP parser, and we get the AST back, right? This memoizing source locator, by the way, is just a performance boost, so we don't keep parsing and re-reflecting the same whole, reparsing the whole thing over and over again, which obviously doesn't make any sense. So given some class structure, like above, right? We've got a class foo, it's got a property bar and a function, and we get the AST that looks something like this. I've simplified it, but to fit it on the slide. And we get all the nodes, all the information that's interesting, like, well, what is the, what's the visibility of our bar property? It's private, and things like that. What are the attributes of it? Well, it starts on line 7 and ends on line 9, and so on. The method node, you get your types, parameters, statements, all the attributes and metadata and things like that. So that allows us to do a lot of introspection and figuring out what's going on. Well, so what can I use Better Reflection for? Well, everything you can use normal reflection for, but if you don't want to go above and beyond that, then you may as well just use normal reflection because it's faster, right? But when we use Better Reflection, we can reflect on files and strings and so on without actually loading them, right? So we can do static analysis using this. It doesn't use any of the internal reflection API, but it does allow us to analyze things like doc blocks to determine types, slowly and surely getting less relevant as we get PHP 7 and we got types and type properties and things like that coming in. But there's still a lot of doc blocks around. So you can use this to do static analysis if you like. You can also do it to modify stuff and do monkey patching. Or what's monkey patching? It's changing how code actually works, right? So you get some code, you change it, and then run it, right? So for example, we get our method foo, it returns the number 5, and we want to change this to do something different, right? So we reflect on the class. If it can be auto-loaded, then we can just use the built-in one. In this case, I've just demonstrated how we can use specific source locators to locate particular pieces of code. Obviously, you have to do this before a class is loaded, because in PHP, you can't unload a class. It doesn't allow you to, unless you're using runkit. Of course, there is always a caveat, but you shouldn't be using runkit in production anyway, right? So then we have this class loader, which is basically Better Reflection's own autoloader. And it wraps up and says, well, if you try and instantiate a class that I'm aware of, that we've called add class on, then it's going to inject its own version of it, right? So if we then say, well, get the method foo, and we want to set the body from a closure, we actually, instead of doing that return 5, we're going to do a return 4. There also exists set body from string and set body from AST, so you could actually make a whole load of AST nodes by hand if you like, or generate them however you like doing that. And replace the method foo's body with something completely different. So when we come to use this class, it returns 4 and not 5. So it's modified, it's monkey patched. So to summarize, for the PHP engine itself, AST is an efficient data structure that is used to represent code. It means faster compilation step, and obviously opcache makes the runtime part of this faster. There's separation in PHP engine for the parser and the compiler. But these concepts, and for me this is the most important thing, is that we can use this stuff in userland to analyze code better. PHP parser obviously exists as a fantastic library for parsing that code. Tools like Better Reflection can use that, and then other tools also use PHP parser, like PHP stan, Execat, which uses its own AST, fan, which uses PHP extension, and so on. So yes, that's what the AST is. Do we have time for questions?
Thank you, James.
Oh.
And we want to thank you.
Oh, thank you very much.
This certificate.
Cheers.
And now we have time for really 2 or 3 small questions.
Okay.
And by the way, in the end, you should vote for the best question, and we will give you, not you, but the person who asked, we will give a book.
Hello, James. Thanks
Hi.
for the talk. Just a quick question. Why do you think if AST is so powerful and we could use it to optimize the code, obviously, during the compile, why don't we still have things like tail recursion unwrapping in PHP?
Because it's a difficult problem space to retrofit into the way the engine works. I don't know enough about why it's difficult to put things like tail recursion in. There are people who would definitely be able to answer that here, like Dmitry probably be able to figure out why, or Nikita, who I imagine both are somewhere around in the conference. Definitely ask them, because they will know.
Okay, thanks.
That's a hard question. I don't know that one, sorry.
Thank you, James. Do you have any other userland examples of using the AST besides code quality tools and crazy compilers? I can think of maybe code generation.
Yes, you can do code generation. I actually did start working on something that generates random code, because the author of Execat, Damien Segway, he said, "Oh, I need something that generates code." And I was like, "Well, we can probably do that by putting some random stuff in there." So I didn't actually finish that, but that would have been cool. But your use cases is primarily going to be static analysis. But yeah, you can do code generation. You could do monkey patching, obviously, as one example. I haven't actually seen anyone using it and saying, "Oh, monkey patching is great," or anything like that, which is probably a good thing. Just because it's there, it doesn't mean you should use it. Yeah, there's lots of use cases for it. It's just kind of how do you actually want to apply that in a way that's useful for you. So.
And we've got time for the last question.
There's one at the back there.
Спасибо. С переводом не поможете? Можете с переводом вопроса? Мой вопрос касается той части, где описывался, как операнды и операторы совмещаются в стэк. И вопрос касается, используется, вот не до конца я понял, используется один стэк для соединения или все-таки используются два стэка? И в чем, как бы, если разница или какой-то приведет к ошибке, если мы будем использовать два стэка для распарсивания уже конечного итога собранных всех операндов и операторов.
I will try to translate the question for you.
Sounded like there's a lot to translate.
The question is about two stacks on your slides.
Mm-hmm.
And the question was actually about did it really use two stacks or just use one stack? And are there any problems if it uses two stacks actually?
what? Sorry.
One stack for operand and one stack for operands. Or it's only one stack for
that's
all of them.
That's one way of doing it, yeah. I mean, there's multiple ways of doing this. This is one example that I explored for writing a compiler. But yeah, there's lots of different ways you can write compilers. That's just one of them. So. Okay.
У нас, к сожалению, нет времени больше на вопросы. Переводить ответ? Или, я думаю, все понятно? Окей. Please, could you choose the best question?
Well, the one over there was a tough one, but I didn't really give a good answer, so I'm going to pick this gent here at the front.
Okay. Thank you so much.
Thank you very much, folks. Cheers.